All right, I'm going to cover two sections, 12.2 more on the center of gravity and 12.3 examples of rigid objects in static equilibrium. And that's mainly examples. I'm not going to go through a lot of them. I'm going to demonstrate a few, but I'll leave it up to you to read the examples. So let's share um, the PowerPoint. Oh, and I'm kind of where I should. I'm not where I should be. Let's see. More on the center of gravity. That's where we left off last one. More on the center of gravity. Um, so this is just kind of a revisit of the chapter 9. We talked about the center of gravity, and you can imagine that you have all these different masses. I mean, this big mass is made up of all these different masses, M1, M2, and M3, and the mass M1 is located at X1, Y1, M2 is located at X2, Y2, and M3 is located at X3, Y3. And typically we can represent the total mass at the center of mass. And so we're going to revisit that, and he's going to take a different approach where we are going to take a G1 for the M1, a G2 for the M2, and a G3 for the M3, where there may be different gravitational accelerations for these different positions. So the center of mass that we learned in chapter 9 is the M1x1 plus M2x2 plus M3x3 divided by the total mass, M1 plus M2 plus M3, so on. So the x position of the center of mass is the sum over all i's of mi/xi divided by the sum over all i's of mi, which is the total mass. Now, notice here how he's compared to this previous image. He's added a G1 vector, a G2 vector, and a G3 vector, assuming that possibly the gravitational acceleration at each of these spots is not the same. And honestly, if you're in a tall enough building, the gravitational acceleration isn't the same. As you go higher in the building, it does decrease by fractions of amount. But this is the exercise he's going through. So we have the M1, M2, M1 plus M2 plus M3 plus on and on and on through M sub however many i's there are, times the gravitational acceleration at the center of gravity times the x position of the center of gravity is equal to M1 G1 X1 plus M2 G2 X2 plus and so on. Now, if we solve for the x over the center of gravity, we're going to get M1 plus M2 plus M3 times G center of gravity in the denominator, and M1 G1 X1 plus M2 G2 X2 and so on in the numerator. Well, if we assume that all of those G1, G2, G3 are the same, then they all cancel out with the G of the CG, and we're left with the original equation that we know. X of the center of gravity is the sum of all the M1s at the XI position and the divided by the total mass. So that fortunately the gravitational constant is pretty uniform over a large area, and so we don't have to worry about that. He's just taking a different approach to getting the center of gravity. Okay, a meter stick of uniform density is hung from a string tied at the 25 centimeter mark. So let me get. Oh well, we won't worry about it. A 5 kilogram, a 0.5 kilogram object is hung from the zero end of the meter stick, and the meter stick is balanced horizontally. What is the mass of the meter stick? So we take this meter stick and we hang it from the 25 25 centimeter mark. Of course, it would rotate like this, but we're going to hang a 0.5 kilogram mass over here, and so it balances. What is the mass of the meter stick? Well, we're balancing it here at 25. The center of mass is at the 50 centimeter mark, which is 25. So we've got 0.25 meters over here with a 50 kilograms, and we've got 0.25 millimeters here, and we assume that it's 0.5 kilograms also, because it balances. And sure enough, that's the answer, 0.5 kilograms. Now, the examples of rigid objects in stable I can't even see in static equilibrium, not stable equilibrium. I was hid by my own face on the screen. Examples of rigid objects in static equilibrium. The center of gravity of the system, the bottle plus holder, is directly over the support point. Just this afternoon, I saw a video of a crane toppling over, and probably what happened is the center of gravity of the crane, with the mass that it was picking up, changed the center of gravity of the entire crane mass system to where it toppled over. If that the center of gravity of that bottle, were just a little bit to either side of that pivot point, it would topple over. And there's different types of stability and instabilities. You can see here, I've got a little ball. This is just the lid to the top to a what I forget what the hot sauce is. It's a particular type of hot sauce, and it's got a little well in it, so I can put this, and it balances very well. And I can even turn it over, because there's a flat side here, and put it there, and it balances. Now, if I were to turn it on its side, there probably is a point where I could exactly balance this. Would that be a stable, balanced position? The answer is no. I might be able to get it for just a moment, but any little agitation, even any little wind, would cause it to fall over. So that would be a very unstable balance position. So it's a high instability. Whereas sitting in this well here, it's very stable, even with blowing on it, putting a little bit of gust of wind, unless it were really strong, it's going to stay stable. And so they go through a whole bunch of exercises to a whole bunch of exercises demonstrating the examples of the rigid objects. They have a seesaw. They have the standing on a horizontal beam, and they have other examples. I encourage you to go through those. And I'm going to go through their problem-solving strategies. Conceptualize, categorize, analyze, and finalize. You conceptualize. You think about the object that is in equilibrium, and identify all of the forces on it. This is on page 314, and I'm just basically reading 314. Imagine what effect each force would have on the rotation of the object if it were the only force acting. You categorize. You can confirm that the object under consideration is indeed a rigid object in equilibrium. The object must have zero translational acceleration and zero angular acceleration. Why is that? Because the sum of the forces, external forces, equals zero, and the sum of the external torques equals zero. So there's no translational acceleration and no angular acceleration. You analyze, you draw diagrams, you label, do a free body diagram, you resolve all forces into the rectangular components, choosing a convenient coordinate system, choose a convenient axis for calculating the net torque on the object. And you solve the simultaneous equations for unknowns in terms of the known quantities. And then finally, you finalize. You make sure that your results are consistent with your diagram. So that's just a problem solving strategy. And then we're going to go on to, so that was actually two sections, 12.2 and 12.3. And we're going to do 12.4 in another video, elastic properties of solids. All right.